Hello everyone. So today we'll look at observability. In last lecture we saw about controllability and like as we saw in controllability, finding the observability is also very easy. In case of controllability, you move from input towards the output. Okay, whereas in case of observability you move from output to the input, so which means that you know the observability of the output already. Okay, and you need to calculate the observability of all the inputs applied to the particular gate. Okay, so this is the case of a NOR gate. Okay, so finding observability is very easy. So let me share it with you. So this C or Z is always given to you. Okay, and you have to add up everywhere, everywhere whenever you want to find out. So this keep this in mind that this is always fixed, that you have to always add this term. Okay, then you have to make another input non-controlling. Okay, so in case of a NOR gate, if see that what is the value of z, a plus b complement, this is the value of z. So if you want to calculate the observability at a, let's say, so c o z, this is fixed, plus then how come this term comes, which it means that b value has to be kept to the 0. Okay, so how how you decide that b value should be kept at 0? So there is a logic behind that. See, if you are finding out the observability at this particular place, hmm, okay, so you have to put another input such that this input is propagated to the output. It doesn't matter that this input is reached as A in the output or a complementer in the output. So this doesn't matter at all. So you have to just look such a way that you get a or a complement. Okay, so if you want to propagate the something in this particular branch input, okay, so what should keep this input b, what you should keep input b, you should keep input, either you have two choices, you can keep input b as 1 or b as 0. Okay, have you got my point? If you keep input as 1, b as 1, then what you will get, you will get z is equal to 0. That means you are not getting a or a complement in the output. Okay, so you cannot put z is equal to b is equal to 1. So only choice left with us is to keep b is equal to 0. Okay, so you have to keep b as 0, which is a non-controlling input. Okay, non-controlling. So cc 0, that means you are keeping b as 0, and plus 1, as we saw in the controllability also, you have to always do it for increase in the level. Similarly, if you look at a also, The same thing applies, same logic applies. You have to put a is equal to 0, okay, in order to propagate this b in the output, okay. So this is the way that how you do, okay. Then another case, in case of the XNOR, okay, what you do in XNOR, you know the observability at set, it is given in the question. Then you want to calculate the observability at a point. So told you that this point has to be fixed. This has to be always there. C or Z. That is the observability of the Z output plus. So what you have to do over here? If you want to, if you want to propagate something in this particular node to the output, how you can do? Hmm, let me do it. See, in case of the XNOR, what you are having, Z is equal to A XNOR B. Okay, so if you put B is equal to 1, you have two choices again. You can put B is equal to 1 and B is equal to 0. Okay, and if you put A B is equal to 1, okay, what you will get? So you know the expression, okay. So you will get A in the output. If B is 0, so what you will get? A dot 0, and you will get A bar dot 1, okay, and you will get A bar in the output, okay, which means that if you put B is equal to 1, so B is equal to 0, in both of the cases you are getting in output A or A complement, which simply means that you are able to propagate the thing in this point to the output, okay. So that is why you are using minimum over here. That means either you can use B is equal to 0, or either you can use B is equal to 1, okay. And minimum, I told you that whenever there are more than one case, then you have to use it like this, and plus one for the increase in the level. Always this term has to be always used like this term, and you have to think of this term only. In the same logic, if you find out the observability at A, in the similar lines, you can calculate the observability at B also, because it is nothing, it is same only, right? What applies to this input applies to this input also only, also. But just also you have to, in case of B, you have to think about A, you have to decide about it, right? Like here we were deciding about B, you have to decide about A in this case, in case of the finding the controllability at B. Then for the NOT gate, see, you are given about the controllability at Z, which is fixed. Okay. Now you have Z is equal to a complement. In order to propagate this a to the output, what you can do, you don't have to do anything. It is always propagated. Okay, it does not depend upon any other input. Okay, it is having a single input. Okay, it will always be propagated. So this is fixed and this is always used. Okay, so you don't have another uh, term to play for. Okay, so in case of fan out, so what is a fan out? Fan out is simply like, here, if you are having a particular gate, okay, you are having a gate and its input is being given to a n number of gates. Okay, here it is gate 1. Okay, so these are nothing but your fan out branches. This These are your fan out branches. Okay, so whenever I told you that here these are your output branches. Okay, and you want to find out the observability at this particular point. So you know the observability at each of the fan out branches. So you have to take the minimum controllability. Okay, minimum controllability. Okay, I hope this is clear to you. Okay, okay, yes. So similarly, we have same examples over here of AND gates. Okay, this AND gate is pretty simple. Okay, you can easily do this. Okay, and if you don't get this, then definitely you can comment in the comment box. uh, this is OR gate. Okay, and NOR gate is also simple. Okay, and you may find XOR to be a little bit complicated, so I will explain this one. Okay, else you can do it easily. Okay, see, in case of the XOR also, if you put Z is equal to A XOR, sorry for the bad handwriting, so A XOR B. Okay, Z is equal to A XOR B. So if you put A is equal to 1, so what will happen in case of a XOR gate? So it will be propagated as Z is equal to, because if you are putting Z A is equal to 1, so that will be equal to B complement. Okay, and if you put A is equal to 1, A is equal to 0, so that will be B. Simple. So in both of the cases, you can propagate uh, this as like this. So uh, COB is equal to COZ. You put A is equal to 0 or A is equal to 1 and plus 1 for the increase in the level simply. Okay. Next is NAND gate. That is also simple. Okay, I hope the idea is very much clear to you. Okay, so in next lecture we will be learning about more complex examples. Okay, so over there we will look at sequential circuits also. First of all, we will take a simple example on controllability, okay, uh, which will be typically a combinational circuit. Okay, then we will move to a sequential circuit also. Okay, so for sequential circuits, the rules are different. Okay, because in case of sequential circuits, you know that you are having like flip flop, wherein you are having a clock input. Okay, you are having a reset input. Okay, you are having a uh, D input. Okay, then you are having a output also. So this is the thing that you are having in a sequential circuit. So in sequential circuit, the analysis altogether a different thing, and it makes the problem very complex. We will eventually see the examples in subsequent lectures. Okay, so I hope you might have learned something out of today's lecture. If you like uh, today's lecture, then you can definitely like the video, okay, and share it with your friends. So thank you very much.